Okay, our last topic in today's lab is one not really specific to support vector classifiers, but these ROC curves, or receiver operator characteristic curves. And they're a way to sort of summarize the performance of a classifier at many different levels. In chapter 4, we saw that for a classifier that, say, predicts probability of being in a class, you could vary the threshold, and that would give you different predictions. And of course, for every different value prediction, there's a different accuracy or a different false positive rate, etc. So the ROC curve sort of summarizes this accuracy as a function of the threshold. Okay. So we're going to use a function. This ROC curve display comes from the scikit-learn metrics package, and we're going to use this method called fromEstimator. So what this does, we're going to give it a classifier that's a scikit-learn estimator that produces something like a threshold of probability that we can use to vary the threshold and trace out a curve of the accuracy as the parameter changes. And of course, I should say that the ROC curve is really meant for binary data, because that's one where you can sort of simply describe the performance of the classifier by the accuracy. Okay, so our estimator, this was the tuned support vector machine we saw just above, and we're going to evaluate, well, we can evaluate an ROC curve on the training data or the test data. First, we'll evaluate one on the training data, and when we evaluate later on test data, we'd expect it to do not as well, and we'll see that as well. Okay, so this makes a plot that has two quantities, two axes, the true positive rate on the y-axis and the false positive rate on the negative axis. So a good classifier is something that's high up in this corner. It has very high true positive rate, that's a measure of the power, and very low false positive rate, that's a measure of the type 1 error or the false positive.
And since this was done on the training data, of course it does really well.
Yes, yeah. And so there's a summary that people provide of the ROC curve called the area under the curve, and that's just the area under this red curve, and it's about 99%. For reference, pure random guessing should be about 50%. So this is quite close to perfect.
And
okay.
And a perfect classifier will get 100%.
Yes. Okay. So we're going to make a few plots on training and test data. We are going to, here we've changed the classifier a little bit, but I want to focus here on the difference between training and test rather than on the classifier. So here we'll fit this new support vector machine on our training data. And of course, it was chosen to be quite flexible. So here's one, as we saw before, a really good classifier can get 100%. Mm-hmm. And well, that's 100% on training data. Of course, we'd have to see how well it does on test data. Okay, so now let's make the same plot, but use test data instead of training data. And we're going to plot it on the same plot by giving it this axis argument. You'll see actually there are a lot of functions around in Python that produce plots that you can give this axis argument to. And remember that the axis is actually the thing where you actually make plots on. So you can use this to add features, to add things to a plot. And most of things like scikit-learn and pandas use this argument, so you can add this ROC curve to an existing plot, for instance. And I'm going to redisplay the figure with this fig dangling reference, and that just produces the figure in the notebook. Okay, so here, instead of the flexible one, we'll look at the plot for the tuned one. And red is the training data, and blue is the test data. And as we expect, the blue one does slightly worse than the red one, because of course it's test data. It still does quite well, an AOC of about 90% here. Okay, so that about wraps up what we're going to discuss today. There's another topic in the lab that is a support vector machine with multiple classes that we encourage you to do offline.